Chapter 9, Section 2 talks some more about chemical equations and how to write them. The chemical equation is just going to describe the type and number of atoms that are going to be involved during a chemical reaction. We will need to be able to write both word and formula equations. So by word equation, I simply mean the actual names that represent these chemicals that you want to utilize in your reaction. So no symbols, just their actual names. So for instance, in this one, ethanol plus oxygen yields carbon dioxide and water. Now if we were to convert that into a formula equation, then we're going to use their symbols. So ethanol would be C2H5OH, oxygen would be O2, carbon dioxide would be CO2, and water would be H2O. So being able to write both word and formula equations will be important. Now, when writing and balancing a chemical equation, it's important to one, realize that it's a trial and error process, and it does take some practice, and it's probably best to begin in pencil in case you need to make any sort of erasing marks. So in this particular equation, I have 2K, or 2 potassiums, plus Cl2, which is chlorine, yields 2 potassium chlorides. So the coefficients within the balanced equation are what help to give us the same amount of elements on both sides. That's what we're using to balance our reaction, coefficients only. Subscripts will never be used to balance the overall chemical equation. So right here, this 2 is telling us that there's 2 potassiums that are reacting. And the 2 is going to apply to everything that follows it. So for instance, this 2 that's in front of the KCl, that applies to both the potassiums and the chlorines. If the coefficient is followed by a subscript, so if you have something like 2 waters, 2 H2Os, then you distribute that coefficient throughout, so they get multiplied through. So there would be 2 times 2 for hydrogen, so 4 hydrogens, and then also 2 oxygens. Now subscripts that you would see are used when you're referring to elements that are part of Bringelhoff, that are diatomic, or if you have an ionic compound or a covalent compound, but that's part of the actual chemical itself. So the 2 subscript here is referring to the fact that there are 2 chlorines because that is part of Bringelhoff. It is one of the diatomic molecules. So any of these elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, or fluorine, whenever they appear by themselves in an equation as opposed to being within a compound, they actually appear in pairs. So it would be Cl2 here. The last type of number that you might see in a balanced equation would be superscripts or exponents, and those are just going to be charges. So for instance, in this one, calcium chloride dividing up or dissolving to split into its 2 component ions. So it would form 2 calciums, and it would form a calcium 2 plus and 2 chlorine 1 minus ions. So that's what the superscripts would tell you. Now just some tips for balancing a chemical equation. One, save hydrogen and oxygen for last if you can. A lot of times by the time you will balance all the other elements involved, these ones might already be balanced, so it can save you a little bit of time. And the second thing is that if you see polyatomic ions on both sides of the equation, you can treat it as if it were one solid entity. So like in this equation, you've got sulfate on the reactant side, and you've also got sulfate on the product side. So we can treat this as if it's one whole unit instead of individually counting out sulfurs and oxygens. The book also suggests that you balance from left to right, so you work your way across the equation just like you would, read the words off the page on a book. And then just finally to make sure that you double check when you're done, because balancing one thing could end up unbalancing something else. And then the last item is if there are charges present, which aren't going to be very often in some of the equations that we use, but sometimes we'll have them. If the charge is present, it needs to be balanced out on the opposite side as well, meaning that the net charge for the reactants needs to be equal to the net charge of the products. In this first equation that I have here for you, it's HCl plus H2O yields Cl minus and H3O plus. Now over here, we can check. We have a chlorine and a chlorine. We have three hydrogens, and an oxygen and an oxygen. So we're already balanced for mass. We have the same number of atoms and same type of atoms on both sides. Now over here, neither of these compounds has a charge, so we're netting 0. Over here, the chlorine gives us a -1 and the hydronium gives us a +1. So those will cancel each other out, and that will also allow us to net a 0 charge. So this equation is balanced. We're finished. Now if you look at this second one, this gives us silver ion and a copper atom that are going to react to produce a copper ion and a silver atom. Now we're already balanced for mass here. We've got a silver on both sides and a copper on both sides, but on this side we're netting a +1 charge for our reactants, and on our product side we're netting a +2 charge. So that can't happen. We have to make sure that they're the same. It doesn't have to be 0, but it has to be the same. So the way we're going to do that is still by adding coefficients. So by putting a 2 coefficient in front of our silver ion, that now gives us a 2+ charge over here, which will balance out with our 2+ on our product side. And if we make 2 silvers on this side, then we also need to put 2 silvers on the other side. And that will not affect the charges here because this is a neutral silver atom. So now we've got the same mass and the same charge on both sides of our equation. So this reaction would now be balanced.